Okay. So I'll go back to the edge physics for my talk. So what I mean by spin-spin coupling is essentially a RKKY interaction, and a very good introduction of that was given by Harv yesterday. So I'll skip most of my introductory parts. So the outline is that I'll discuss very shortly what is, just to remind you, RKKY interaction is. So the known results of RKKY interaction in quantum Hall, quantum spin Hall edge, integer quantum Hall edge, it vanishes. That I will show how. Then I will show what happens if my geometry is finite, that the edges can come back through the finite geometry. And essentially we'll analyze a little bit of that. And I'll give a proposal to control the RKKY interaction in this geometry in a very non-local way, a completely non-local way. In a way that I will not perturb anything in the spins or anything in between the spins, okay, far from the spins. And some implication of some of the things in cases like Weyl semimetal, which I'm not going to bring up too much. It's not part of, I think, the theme of the conference. Okay, so this is the SD exchange coupling that Harv was talking about, that if I put a spin in an environment of a conducting electrons, then this is exchange interaction between the spins and the electrons, giving rise to the SD Hamiltonian, which couples the spin with the underlying electrons. And if I put a second spin at some distance apart, the second spin will also be coupled to the underlying electrons. And if I integrate out the underlying electrons, one would get an effective interaction between the two impurity spins that you have put on the underlying electrons. So these Green's functions sitting here, this is a second order perturbation result of the RKKY interaction. And these Green's function are the Green's function of the underlying non-interacting electrons. And they carry the information of whatever the state of the electrons underlying system has. Yeah, and as Harv said, this is a very interesting phenomena, and it gives rise to magnetic orderings of the spins in an otherwise completely non-interacting environment. So particularly what interests a lot of people in the community is also to look for how to control these interactions. And a lot of works on optical control of RKKY interaction through magnetic and electric fields. So a lot of relevant works and a lot of experiments as well. So one experiment that came up a couple of days ago, I haven't read this, so don't ask me about it. But broadly, this is about controlling the coupling between two impurity spins through RKKY interactions. It has implications in spintronics and other futuristic applications. Okay, so now going back to the topic of my talk. So RKKY interaction in quantum Hall, quantum spin Hall edges. So as this conference made everyone very clear that a quantum Hall edge has at least one channel of electrons, and where both upspin and downspin electrons move in one single direction, whereas quantum spin Hall edge has two channels where upspin electron move in one direction and downspin electron moves in the other direction. So this is a very simplified Hamiltonian of the edge mode. I mean, you can write it down because the bulk has a gap, so your low energy excitations are only coming from the edge. Now, what turns out is that if you put two spins, some distance apart, coupled to the edge in a very simplified manner, of course, the coupling itself can be very complicated, as Moshe was talking about. But in a very simplified manner, if you put two spins on the edge of the spins, the coupling becomes vanishes at least in second order for the case of quantum Hall. And the Ising part of the coupling vanishes in the case of quantum spin Hall. This is a known result, and I will briefly tell you why. Okay, let's discuss a little bit of why it vanishes, because we want it to not vanish, and we'll see how we can circumvent the vanishing part. Okay, so as I said, so let's take a quantum spin Hall. So this is the Hamiltonian of quantum spin. The sigma z is written in terms of upspin downspin basis. So it tells you that you have velocity of positive x direction for upspin and negative x direction for downspins. And you can write down the Green's function in the basis. So this tells you again that you have positively moving and negatively moving modes for up and down spins. Okay, you can do a Fourier transform of that. So I mean, as you expect, this is a retarded Green's function which couples essentially or which carries information on one direction for upspin and other direction for the downspin, right? So that's supposed to happen. For a quantum Hall system, you would expect exactly opposite. I mean essentially up and downspin both will carry information with only one direction. So that this theta function it basically tells you that you can only carry information from one side to another side, not the other way around. Okay, so this is essentially a block diagonal Green's function with some coefficient here, and they have some theta functions. Now this was the RKKY integral we wrote, and let's say this is my g of r, some p and q, and this is my g of minus r, p prime and q prime. So what is interesting is that sometimes is intuitive to think the following way, that g of r is carrying information between the spin I to spin j, and g of minus r is carrying information back from the spin j to spin I. So essentially you want to go from I to j and come back, okay? And this Green's function are doing that. Now for quantum Hall, as we know that only one of them will survive out of the two, so both p prime and q prime will be 0, and quantum spin Hall, q and p prime will be 0, right? So one spin will go in one direction. So you can put it back, this form of Green's function into this integral, and you will get a form of RKKY which has this the so-called Heisenberg term, the Ising term, and Dylogensky-Moria term. Now, Ising term has a form like this, Heisenberg term has a form like this in terms of this fictitious p and q, okay? Now, it's very easy to see for quantum Hall, if I put p prime and q prime 0, all of them will go to 0, okay? And quantum spin Hall, you will again understand that only this term will go to 0 if I put q and p prime to be 0, other two will survive, okay? So this tells the essential result that for a quantum Hall edge or quantum spin Hall edge, the RKKY interaction, the second order coupling between the spins vanishes for quantum Hall, and only the Ising term, which is the most important term, this is the natural spin directions, vanishes for quantum spin Hall. Okay, now we'll slowly go over to it, but let's try to see how that we can verify this easily. So this is a very simple model of a quantum Hall, quantum spin Hall without invoking a magnetic field. So you can think of it as an anomalous quantum Hall. The problem with magnetic field is you have degeneracies and stuff which will just complicate the matter. So without a magnetic field, this is a hexagonal lattice very similar to graphene. This T is a hopping between, sorry, I think I put it exactly wrong. So that this should be lambda, this should be T. So T is a nearest neighbor hopping which couples nearest neighbor atoms. And this should be lambda, which are next to nearest neighbor hopping, okay? And the point here is that the lambda, so my notation is wrong, this should be lambda, this should be T. The lambda should be such a way that it should be of opposite sign for moving in a clockwise direction or going in anti-clockwise direction, okay? So in that way you are breaking time reversal symmetry. Now, if the lambda is the same for both up and down spin, then you break time reversal symmetry, you get a quantum Hall state. So you have a gap which is of the order of lambda. If the lambda is of opposite sign for opposite spins, so each of them are also doing oppositely for clockwise, anti-clockwise, then overall you don't break time reversal symmetry and you get a quantum spin Hall. So you get essentially two copies of quantum Hall with opposite spins, okay? This is one of the simplest model you can think of for the system. Okay, so now you can make a, this is a quantum spin Hall, because for quantum Hall all couplings go to 0, so no point of showing them, right? Quantum spin Hall, you can put two spins at the edge, so there is a H channel going there. It doesn't really matter where exactly you put A or B sublattice. You get some coupling for all other terms except the JZZ, the rising term, which vanishes. So it's like several orders of magnitude smaller than the others. So there's some arbitrary energy, scale I don't care about here. So this term is way smaller than, so this is of the order of numerical accuracy that you can do. So this obviously makes sense that it should happen. Now what happens if we are in a finite geometry? So where the edge states are going along and can come back through the whole, traversing the whole system. This is the result we get. So apart from having other whatever spin components you had, now you also have a finite and a constant Ising coupling. Okay. So the result is the following. Summarize is that in a finite geometry, that was I was showing for quantum spin Hall. If you do for quantum Hall, you get all the diagonal components non-zero and same values. So quantum Hall or quantum spin Hall, whatever was 0 before is not 0 anymore, is distant independent, and in these cases I see antiferromagnetically coupled. I mean, so it must be coming from the fact that that intuitive picture that I told you, that if the two spins can, you have to go the information there and come back, and which was prohibited in quantum Hall because it can only go in one direction. Now in a finite geometry, they can also connect through this longer path. That must be the reason why this coupling becomes non-zero. Okay, so we can verify that with a small analytical exercise. So this is a Hamiltonian, which is this tau is another Pauli matrix we write. So this is a Pauli matrix of an orbital degree of freedom. Okay. Now you couple to this Hamiltonian with some spins that I'm not too interested at the moment. You can think of for spin up it's positive, for spin down it's negative. For each spin you can write a Hamiltonian like that. This is a simple Dirac equation. And we know that if there is a boundary between a sign of m between, for example, in a disk, the sign of m is negative and outside disk is positive, then at the boundary you will get some modes which are within the gap of m. Okay, so this system is a Dirac equation which has a gap of m, m or 2m. And if you have a boundary between positive and negative m, then you get some number of edge states. So these edge states are now characterized by angular momentum. They are basically wrapping around the disk, and the angular momentum, let's say n, then the energy of these states are essentially Vf by r n plus half. So this is the result when you have a thick enough, large enough disk. Okay, so my edge states are now Vf by r n plus half. So the n is now discrete. Previously we had a kf or kx, and the kx was a continuous variable. Now it becomes a discrete variable. So what you expect vaguely is that, so this is the way this Green's function will now connect between a point which is sitting on the perimeter and another point on the perimeter which has a azimuthal angle phi. So this is the Green's function, it connects them. You can exactly solve it. This Green's function is an approximated form, but you essentially, you can think this is the correct expression. For so essentially for a quantum Hall, they have a single sign of energy. For a quantum spin Hall, depending on the spin, they have opposite signs of energy. That's it. Okay, so let's look at quantum Hall. I do not have a defined sign of energy for up and down spin, and essentially this is the Heisenberg part of the coupling. You put it back, you get expression like that. So a couple of things to look here. One is these f's are nothing to worry about. There are some wave function overlaps, and they do not really depend too much on m and n. So most of the summation comes when m equals to n, okay, which makes it completely phi independent. Okay, so this is one way to think how this coupling becomes phi independent. Distance independent. So the distance is now represented by r times phi. And the coupling also has a 1 by r square sitting there. So the 1 by r square is something which is only for those coupling which were originally absent. Like the quantum Hall, all the couplings are originally absent, now they become finite and has a 1 by r square. For quantum spin Hall, only the Ising coupling will have a 1 by r square, other will not have a 1 by r square. So this is one way to distinguish them. So if you change the size of a system, this is for a finite Nano-Ribbon, only one of the coupling goes as 1 by r square, which is the Ising coupling for a quantum spin Hall. Right. So we made it more we initially had some tight binding results. Now we brought in some analytical calculation, and essentially did not solve much except the fact that we get some expression. We say, okay, m equals to n contributes more. It makes phi independent. So we can also look at it from a more physical perspective. Why this coupling becomes phi independent. So let's look at the Green's function now. It's a very simple Green's function, and let's ask for the quantum Hall Green's function, what is g of x1 minus x2 and what is g of x2 minus x1. Okay. For the infinite 1D line of quantum Hall edge, we know that only one survives. There was a theta function. Now this is a edge, a perimeter of a disk, and question is, do one survive or not? And as you can imagine, for a very small eta, so there is essentially no decoherence, if you wish. Both of these components are exactly same. As we increase eta, this slowly, the state becomes more and more chiral. So the path which connects this gets lost, and path which connects the smaller distance survives. Okay, and this is a log scale, so it survives for a range of eta. So the physical understanding of this eta is actually very simple. So when essentially this eta is what eta does? Eta gives a finite lifetime to your state, and
yes, already.
Right.
So eta is not.
Yeah. Well, right. It's a parameter. Yeah. 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 So it essentially is a finite lifetime of your. There's a very cumbersome way of understanding zeta for a finite geometry, but yeah. So essentially, it gives a finite lifetime. So you can estimate how much is the mean free, or what do you call the corresponding finite the distance that it will traverse in a finite lifetime. So if the perimeter is smaller than the distance, okay, then it can completely traverse the whole path, and then both of the g becomes exactly equivalent. When this the lifetime is large, so lifetime is should I say large or small? Small. So eta is large, right? So eta is large, the lifetime is small. And the mean free path, if you wish, is smaller than 2 pi r, then this state cannot come back, and essentially you see this very chiral behavior that the Green's function can only connect in one direction, not the other direction. Okay, so this eta has a very complicated meaning in our calculation, which we are putting just as epsilon. Right? So for any epsilon you put, there will be a finite distance after which you will see that there is a difference between. So the essence of saying that the coupling is distance independent is modulo the fact that we are taking a very small eta. So as soon as we start taking larger eta, of course, it will become distance dependent. And of course, everything is bound by the system size you have, the Kondo cloud size you have, etc., etc. Okay, so this gives a interesting idea about controlling the eta, and thus going from this regime to this regime by attaching a lead far from the system. Okay, the idea is actually very simple. I mean, your quantum Hall geometry, for a large enough quantum Hall geometry, you know that quantum spin Hall, the RKKY interaction was vanishingly small. You make it finite, it's a finite amount. Attaching a lead far from them can basically absorb the state or decoherent the state completely in the lead. And the new state which is coming back from the lead are completely not in coherence with the original state. Right? So in that way, you can completely control the coupling which is happening between these two spins by attaching a lead far from them, however complicated the experimental setup would be. Okay, so this is a very, very simple exercise. You essentially model the Green's function with the self-energy coming from the lead. Self-energy contains the density of states of the lead. So essentially, if you just approximate density of states to be independent of frequency, so a flat band limit, you see that with increasing density of states, this coupling vanishes exponentially. Okay, and that is what you expect. Essentially, increasing density of states gives you finite lifetime of the state, and yeah, it essentially vanishes. So this is a very nice thing. So this is the coupling which was originally non-zero for a quantum spin Hall. This is not affected at all by whether you put a lead far from it or not. Whereas the coupling which was originally not present is present only for a finite geometry, vanishes exponentially as you put it lead. I mean, one can also think, okay, one can ask, okay, this is an unrealistic situation partly because you put a lead which is of a very large bandwidth and it can have unintended consequences. You can also put a lead of very small bandwidth of the order of the gap of your quantum Hall system. And if you put so this is essentially showing you if this rho has a omega dependence, so up to omega equals to omega c, let's say. So once your omega dependence is such that, so the bandwidth of the lead is such that so this is the 0.4 is the bulk gap. Once it crosses or close by 0.4, this coupling, this is also a log scale. Well, I don't think it is. Anyway, it also vanishes as you grow, close to the gap. Anyway, so the take-home message of this part is that essentially you can control this coupling between two spins. Okay, and so these spins can be in purity, but in this case, I'm not thinking of impurity coupling. We can also think of controlling the magnetic states of a lot of spins sitting here by putting a lead far from it. But even like few spins you have and you want to control the coupling between them, this could be one way of, but although the question is how do you change it dynamically, the coupling to the lead is also a complicated question. That can probably be done with some frequency and stuff like that. Anyway, so this is a kind of just showing off a plot that if you have a lead attached to it, you basically restore back your old result. So this result you should compare with the one we had. We had a finite JZ. The others were, basically present. This was only because of finite geometry. Now, if you put a lead, this is a really far from the spins. You basically kill off the extra coupling that you generate. Okay. Now, this is any question up to here? Yes.
So I want to ask is why these are the oscillations in these JXX and XY? Yeah.
Okay. So these oscillations are the 2kFR oscillation coming from cone anomaly that Harv was talking about. So we have a finite. Okay, this is very important in a sense that I forgot to mention one point. So this coupling does not oscillate. They do not oscillate with 2kFR. I mean, the mechanism is different. Whereas these couplings, they oscillate with a 2kFR oscillation. So once this coupling is determined, whatever the sign of it is, it remains fixed for irrespective of the distance. So to answer your question, these oscillations are 2kFR oscillations. Yeah.
Sorry, I thought you were in a quantum Hall state.
Yeah, these are the edge.
Where's the Fermi momentum?
Oh, this is the edge. This is the edge. The edge has a dispersion. It's a dispersion of the edge. Right. So quantum spin Hall, you have up spin and down spin, which forms a KF.
They're separated by.
Yeah, the KF. Yeah. So if you put KF to 0, of course this oscillation will die out. Any other question? Okay, so I'll also finish relatively fast. So this part is supposed to be short, but let me make a slightly longer introduction as we have time. So this is a one slide introduction to Weyl semimetals, the word which has not been spoken so far in the conference. Right? So essentially, you can think of a Weyl semimetal like you have a original some Dirac equation or Dirac cone, and you break some symmetry, and you separate the Dirac cones into a set of Weyl cones. Okay? So in this particular case, I'm thinking of breaking a time reversal symmetry and separating them in momentum space. You can break inversion symmetry, which will also generate two Weyl nodes. And so on. So once you are in a Weyl semimetal phase, these nodes cannot be gapped out anymore by any perturbation. Okay? I mean, you simply used up all sorts of Dirac Pauli matrices you can use, so you cannot bring another one to open a gap. Unless you break charge conjugation or introduce superconductivity, then of course they will open a gap. So of course I'm thinking of perturbations which does not scatter between one Weyl node to another Weyl node. If it does, then it will also open a gap. So essentially the bulk of a Weyl semimetal would be a system where you have a lot of such Weyl nodes which are diagonal. So your bulk will not connect between the Weyl nodes. So each of the Weyl nodes will contain Weyl excitations near the Weyl nodes. Now what is interesting is that, so this bulk H1, H2 to H2n, these Hamiltonians, each of them are some Weyl equation. And bulk is not connecting them, but as soon as you put a surface, the surface has a way to understand essentially connecting one to another pairwise. Right? Essentially the surface will pairwise, connect is a bad word, but let's continue with that, will pairwise connect these various Weyl nodes in a way that you get surface states between one Weyl cone to another Weyl cone pairwise. Okay? And this surface states lives only on the surface of the three-dimensional system. So essentially you can think of the surface states are like if you have a cylinder and the Weyl nodes are along the axis of the cylinder, the surface states are wrapping around the cylinder. So this is you can probably observe there has been a lot of observations that there might be Fermi arcs that people can observe if you look at surface momentum and do some RPS experiment. This is when the chemical potential is exactly at your Weyl nodes. Now, if you shift your chemical potential, these surface states will disperse opposite in opposite surface. Okay, and so this one of the top surface states will disperse this way, bottom surface will disperse this way. So this is the arc here because the other part of the Fermi surface is on the bottom surface. Okay. So this constitutes the basic ideas of Weyl semimetal, that you have a Dirac equation, you break into Weyl equations which are diagonal in your bulk. The surface connects pairwise, and pairwise you get Fermi arcs, which has opposite dispersion in opposite surface. Okay. Right. So now for a slab geometry, we have to know which are the Weyl nodes which are being connected by the surface. Right. So you can, out of the 2n number of Weyl nodes, you can basically pairwise collect all the Weyl nodes. Now, so in this particular case, we are going to ask a question that what happens if I put two spins on the same surface of the Weyl nodes? Actually, I did not put result of this. This is also we have. I thought I will use up all my time. Anyway, so we are asking question of exactly the same question that we asked in quantum Hall, that these states are essentially reminiscent of the quantum Hall nature of the underlying bulk states of the Weyl nodes. So the bulk states of Weyl nodes are essentially gives a quantum Hall state for various values of this momentum kx. Okay? And these surface states are nothing but the quantum Hall states of this projection of the bulk states. So essentially you have a lot of set of quantum Hall states running along the surface. Actually there might be multiple sets of them coming from different Fermi arcs. For each of the Fermi arcs you have a channel of surface states. So in this very asymmetric anisotropic system, if you put two spins, the question is how do they couple, and whether their coupling has the effect of the thickness of the sample, right? So just few more words about it. So the Fermi arcs are not only they disperse along opposite direction, they are also spin polarized in certain spin basis. I mean, there could be some pseudo spin. I mean, there could be some pseudo spin with some angular momentum, but for the simplicity, we'll take them as in the basis of a spin half. They are spin polarized in a relevant basis. They move in opposite direction. So if I have one Fermi arc, so only two Weyl nodes, then the surface spin density will be, there will be a net surface spin density, okay? Which is bad because the RKKY interaction is only the relevant interaction, only if your underlying electrons are not polarized. So to discuss about RKKY interaction, you need at least two Fermi arcs, so the surface remains spin unpolarized. Right, so we need at least two Fermi arcs. Actually, we can have a set of two. Typical, many of the materials have multiple Weyl nodes, so set of multiple Fermi arcs. For the very simple case of, let's say I have four Weyl nodes and two Fermi arcs, the Fermi arc wave functions are something like this. I mean, the only part you can recognize is this term, which tells you that the wave functions decay in the bulk with some mass term. So turns out the surface Green's function is 1 by r along the direction they couple, makes sense. And the direction which is opposite is a very small, it goes much faster, and bulk also it decays fast. So we'll basically look into spins which are only in the surface and coupled by the strong, essentially very strong coupling by the, essentially it's a 1D physics you're looking at. Although you're sitting in a 3D, in a 2D surface of 3 dimension, essentially looking at a 1D physics. Okay, so this is one of the results we have, and so assume that your Fermi arcs are polarized in sigma x, okay? Some spin direction sigma x. So as soon as it's polarized sigma x, you can think of a lot of quantum Hall states which are running along the surface. Each of these are polarized on sigma x, okay? And they have a single chirality, which tells you that jxx should be vanishingly small, right? And this is what you find as you increase the thickness, so the Fermi arcs are better formed, the jxx term goes to 0. We are also using some other technologies of some recursive Green's function which involves two surfaces, etc. But essentially, we can see that the jxx vanishes exponentially. So this is exponential, this is a log plot, whereas I'm changing my L almost linearly, and it decreases exponentially. So what it means that with increasing thickness, the jxx vanishes exponentially. Okay? Now, why does it vanishes exponentially gives a important question. That jx is whatever jx is remaining, the contribution can come from two sources. The Fermi arcs are not going to give any jxx; they are polarized in x direction. So jxx can come from either the bulk states, or can come from the other Fermi arc, which is there in the opposite surface. Okay. So it's like a similar feature that you saw, that something can go and come back only through the other surface. Now, what we believe is that if this was coming from the bulk states, there was no reason that this term should go to 0 exponentially, right? I mean, after some thickness, your bulk is essentially not affected. Local properties of bulk are not affected. So the reason it's going to 0 exponentially tells you that this finite contribution jxx you're getting is essentially the same physics of having two Fermi arcs on opposite surface. Anyway, one can also look at their distance dependence and so on. Not going to discuss much about it. In fact, this is my last slide. So essentially, I talked about how RKKY interaction can capture some of the underlying physics of the bulk states, especially this is a topological state. RKKY interaction finite geometry helical edge is non-vanishing through non-local processes. So essentially, you need processes which can traverse the whole edge. Opens up possibility of controlling such coupling non-locally. And essentially, RKKY in Weyl semimetal is supposed to be very interesting as it looks like. Okay, so with that, I finish my talk.